Hi, I'm Isaac, and I'm talking about polarization. I'm filming from my house because I'm under quarantine, thanks to the virus. Okay. Now polarization. You've probably heard of this before, but most likely you've heard of separation of charges. And this is a different type of polarization. This is more in reference to light. It's more the type of polarization you see with sunglasses and with other types of materials, right? If we were to define polarization, it's defined as the action of restricting the vibrations of a transverse wave, especially light, wholly or partially in one direction. Okay? So if you look at light, it's made of two components. It has the electromagnetic portion and the magnetic portion. Okay, today we're just going to be focusing on the electromagnetic radiation side, right? That oscillation in one direction. Okay? Your sunglasses, they're polarized because they're made up of millions of little molecules in such a way that when the light hits your sunglasses, it is directed, it is restricted in a way that we can alter this electromagnetic portion of the light wave, right? And I'll show you that really quick. Watch. Okay. Now I just have a rope, right? And we can use this to model what a wave looks like. When it oscillates, it can go in one direction, right? It can go up and down, or it can go side to side, right? In all directions can oscillate. Lots of fun stuff. That's a wave. What polarization is we modify that wave. So I just have this tool, right? And it has like a slit, horizontal slit here. If I get this rope and I put it through that slit, then it behaves differently. Okay? If I go horizontally, then it oscillates just fine. Okay? But if I go vertically, which is in direction opposite to the slit, look what happens. So you can see that the oscillation happens right here, but once it hits this filter, it stops. We don't see any vibration on the other side. Sorry, there's some glare on that. And this is a great way we can look at light in general, right? Light is made up of a bunch of different components, right? Light is oscillating in different directions. This is natural white light we see, like sunlight. Now, if we take this light, I just drew it in different colors, right, to represent kind of like the different directions, kind of like different components. If we see it and we bring it through a polarizing filter, we see that only one component is left over. The component that is in the shape of that direction, right? That is matching the direction of the filter. Now we have this polarized light. We can actually bring it through another filter, and that's where we can start to do some really fun stuff with it. That's where we can get creative. Now, if I take this light and I put it through a filter of the same direction, nothing happens. Okay? It could go through a million filters of the same direction, and it's going to be the exact same because nothing's stopping it. Right? If I put this light through a filter that is perpendicular to the first one, then nothing is left over. All of the light gets blocked, and we don't see anything, right? It would be black. If I get this light and I put it through a polarizing filter that is in between, then it reduces the intensity, right? I kind of drew that. It's just smaller. Okay? We can actually deduce mathematically how much of this component is left over. Okay? Let me go over here. And this is the equation we use. It's I is equal to I naught cosine squared theta. Okay? I is the resultant light, the leftover light. I naught would be the original light you have, and theta is the angle right here. Okay. Now let's say, for example, we wanted to reduce the intensity of a certain light by 90%. Okay, if we wanted to reduce the light by 90%, it would mean that the resultant light would only be 10% as strong as the first light, which would mean that I would be equal to 0.1 I naught. Okay, I naught is only 10% as strong as I is only 10% as strong as I naught. Okay. Mathematically, or algebraically, excuse me, we can get this. Cosine of theta is equal to the square root of I over I naught, which is also equal to the square root of 0.1 I naught over I naught. Okay. Mathematically, we get 0.3162. Now, using that, we can plug it into our master equation up here and get theta is equal to cosine squared 0.3162, and then we get 71.6 degrees, which means that if we take light that is oscillating in one direction and we put it through a polarizing filter, kind of like that, and the angle between the two was 71.6 degrees, the resultant light would only be 10% as strong, or we would reduce that original light by 90%.